Listen closely to that sound. It's not a melody from our world, but the steady, rhythmic heartbeat of a cosmic lighthouse, a pulsar spinning in the void. That sound is a direct signal from one of the most powerful and invisible forces in the universe, a force so immense it can warp the very fabric of reality around it. Across the cosmos, in the most extreme environments imaginable, magnetic fields operate on a scale that defies human comprehension. They are the silent architects of the universe, the cosmic superpowers that can twist a star into a pretzel, accelerate particles to nearly the speed of light, and create conditions so bizarre that they challenge everything we know about physics. These fields are not just gentle nudges, they are titans shaping the birth and death of stars, governing the behavior of entire galaxies, and hiding secrets in their invisible grasp that we are only just beginning to unravel. Today, we are embarking on a journey to explore these fundamental, ferocious forces. We're going to dive deep into the heart of magnetic monsters and uncover 30 incredible facts about the universe's most extreme magnetic fields. This is not just a list, it's an expedition to the farthest reaches of space and the deepest principles of nature, where the rules are written by forces strong enough to tear atoms apart. Imagine standing on the surface of a magnetar, a type of neutron star with a magnetic field 1,000 trillion times stronger than Earth's. From that single, unimaginable vantage point, the entire concept of magnetic is rewritten. Your very atoms would be stretched into thin, needle-like shapes. The empty space around you would boil with particles and antiparticles created from pure energy. This is the raw, untamed power we're talking about, a power that exists not in science fiction, but in the documented observations of our telescopes and the theoretical work of our brightest minds. It's a realm where physics becomes fantastical, and the universe reveals its most dramatic and violent performances. So, as we begin this journey, prepare to have your perspective shifted. We'll move from the familiar pull of a fridge magnet to the mind-bending realities of magnetic fields so powerful they can literally bend light. We will uncover how these forces are not just destructive but creative, seeding the universe with the elements for life and sculpting the cosmic structures we see in the night sky. This exploration is about connecting the dots between the fundamental forces that bind our reality and the spectacular phenomena that illuminate our universe. Get ready to discover how these invisible cosmic titans hold the keys to some of the greatest mysteries in existence, and why understanding them is crucial to understanding the story of everything. To understand these cosmic monsters, we first need to grasp the fundamental idea of a magnetic field. Think of a simple bar magnet, the kind you might have stuck to your fridge. That invisible force that pulls a paperclip towards it or pushes another magnet away, that's the magnetic field at work. It's an invisible region of influence surrounding the magnet, a kind of force field where magnetic forces can be felt. At its heart, this phenomenon is created by the motion of electrically charged particles. On Earth, this happens deep within our planet, where the churning of molten iron in the outer core generates electrical currents, which in turn produce our global magnetic field, a protective shield that deflects harmful solar radiation and guides compass needles. Now take that same basic principle and launch it into the cosmos. Out there, the ingredients become far more dramatic. Instead of molten iron, we have vast oceans of searing plasma, the fourth state of matter where atoms are ripped apart into charged particles. When these immense, superheated, electrically conductive fluids move, they can generate magnetic fields on an almost unimaginable scale. This self-sustaining process, known as a dynamo effect, is what powers the magnetic hearts of planets and stars. But the fields we're about to discuss are not just larger versions of Earth's. They are entities of a completely different order, born from the most violent and dense conditions the universe can muster. We are leaving behind the familiar realm of planetary magnets and stepping into a domain where the very rules of physics are stretched to their absolute limit. But if our own planet's magnetic field feels impressive, it is a faint whisper compared to the cosmic scream of a magnetar. To meet the undisputed champion of the magnetic universe, we have to travel to the aftermath of one of the most violent events in existence, a supernova. When a massive star, many times heavier than our Sun, exhausts its nuclear fuel, its life ends not with a whimper, but with a cataclysmic explosion that can outshine an entire galaxy. What remains after this stellar detonation is not nothing, but an object of almost incomprehensible density, a neutron star. Imagine taking a star more massive than our Sun and crushing it down into a sphere no wider than a city. A single sugar cube-sized piece of this material would weigh as much as a mountain. Now, take that already bizarre object and subject its formation to a perfect, violent storm. During the supernova collapse, if the star's core is spinning rapidly and its internal magnetic field is perfectly aligned and concentrated, something extraordinary happens. That inherited magnetic field, squeezed into such an unimaginably small and dense object, becomes amplified to levels that defy logic. This is the birth of a magnetar. The numbers involved are so vast they lose all meaning without a point of reference. A typical magnetar possesses a magnetic field that is a quadrillion times stronger than Earth. To put a quadrillion in perspective, it's a 1 followed by 15 zeros, 1,000 trillion. Let's make that power tangible. Suppose a magnetar were to appear in our solar system, positioned halfway between the Earth and the Moon. From that distance of nearly 200,000 miles away, its magnetic influence would be so profound it would wreak havoc on our modern world. The magnetic strip on the back of every credit card on the entire planet would be wiped clean in an instant. But that's just the beginning. Its pull would disrupt the fundamental physics of our world, distorting the orbits of satellites and potentially interfering with the very chemistry of our atmosphere. This isn't a gentle force, it's a fundamental reshaping of the local environment by sheer magnetic dominance. The existence of these objects pushes the very laws of physics into uncharted territory, creating conditions so extreme that we cannot replicate them in any laboratory on Earth. A magnetar's field is so intense that it twists the very fabric of space and time around it, in a phenomenon predicted by Einstein's theory of general relativity. The vacuum of space itself is no longer empty near a magnetar. It becomes a roiling sea of virtual particles, stirred into real existence by the sheer power of the magnetic field. This is a realm where matter is forced into strange, elongated shapes, and where light itself is bent and polarized, creating a reality that is as terrifying as it is fascinating. That almost incomprehensible density is the absolute key to unlocking the mystery of a magnetar's power. To truly appreciate the forces at play, let's take a closer look at what a neutron star actually is. Picture our own Sun, a massive sphere of searing hot plasma over 860,000 miles wide. Now, imagine the force of gravity at the end of that star's life, taking that entire immense structure and collapsing it inward with unimaginable violence. The star's own weight crushes it down until it's only about 12 miles across. All that mass, more than our entire Sun, squeezed into a space no larger than a city. This creates an object so dense that the very nature of matter itself is fundamentally altered. Under normal conditions, an atom is mostly empty space, a tiny, dense nucleus surrounded by a cloud of electrons whizzing around it. But inside a neutron star, gravity wins a total victory over that emptiness. The colossal pressure is so extreme that it overwhelms the forces that normally keep atoms apart. It forces the positively charged protons and negatively charged electrons to merge, cancelling each other out and transforming into neutrons. the entire star becomes a giant, city-sized atomic nucleus, a solid mass of neutrons packed tighter than anything else we know of in the universe. This is where that famous comparison comes to life. If you could somehow scoop up a single sugar cube-sized piece of a neutron star and bring it to Earth, it would not simply be heavy. It would weigh approximately 1 billion tons, as much as every single human on the planet combined, or the entire Mount Everest. This isn't just dense rock. It is the fundamental building blocks of atoms stripped of all their space, pressed shoulder to shoulder in a state of matter that cannot exist anywhere else. And it's within this incredible, hyper-dense environment that the magnetic magic happens. The original star that collapsed had its own magnetic field, a vast, diffuse web of magnetic influence spread throughout its enormous volume. When that star collapses, that magnetic field gets caught in the crush. Think of it like a gigantic, invisible spider web. If you take that vast, wispy web and compress it down to the size of a marble, the individual strands of the web don't disappear. They become incredibly concentrated and powerful. This is the dynamo effect on steroids. The rapid spin of the newborn neutron star, combined with the frantic, turbulent motion of its superfluid interior, acts like a cosmic generator, amplifying that already concentrated magnetic field to ludicrous levels. The incredible density provides the perfect conduit, a sea of charged particles without the empty space to slow things down, allowing the magnetic field to intensify to a level 1,000 trillion times stronger than our planet's. So, the very existence of a magnetar is a direct consequence of this ultimate density. It is the crucible, the extreme environment where the ordinary rules of physics break down, allowing for the birth of the universe's most formidable magnetic force. So we have this city-sized ball of neutrons, held together by unimaginable gravity and riddled with a magnetic field of pure titanic force. But this setup is anything but stable. It's a pressure cooker, and the result is some of the most violent seismic activity in the cosmos. On Earth, we have earthquakes caused by the shifting of tectonic plates. On a magnetar, they experience starquakes. The surface or crust of a neutron star isn't like a soft, gaseous surface of a normal star. It's thought to be a crystalline lattice, a shell of iron nuclei packed into a rigid, incredibly strong solid, perhaps 10 billion times stronger than steel. Yet, even this super-strong material is no match for the internal forces at work. The magnetar's incredibly powerful magnetic field isn't just a passive aura, it's a dynamic, living entity. The field is under immense stress, tangled and twisted by the star's rapid rotation and the turbulent motions deep within its interior. This creates an intense, relentless pressure on the solid crust, bending it, straining it, looking for any point of weakness. It's like wrapping a steel ball in increasingly taut rubber bands. Eventually, something has to give. When the strain becomes too great, the crust of the neutron star suddenly fractures and shifts. This is a starquake. The energy released in this single event is staggering. In a fraction of a second, a starquake can unleash more energy than our sun will emit over 100,000 years. This cataclysm doesn't just shake the star, it has a direct and spectacular partner in crime, a process known as magnetic reconnection. To understand reconnection, picture the magnetar's magnetic field as a series of incredibly tense rubber band-like lines arching out from its surface. These lines are frozen into the super-dense plasma of the star. During a starquake, the sudden movement of the crust violently snaps these magnetic field lines, breaking them like overstretched elastic bands. But they don't just disappear. Immediately, the broken ends desperately seek a new, lower energy configuration. They frantically reconnect with other broken lines in a different arrangement. This sudden reconfiguration is like cutting a tensely coiled spring. All the pent-up magnetic energy has to go somewhere, and it's converted explosively into an intense flood of radiation, primarily gamma rays and X-rays. This 1-2 punch, the crust cracking and the magnetic field snapping, creates a flash of light so brilliant it can be detected across the galaxy. In 2004, on December 27th, satellites orbiting Earth were momentarily blinded by a massive wave of gamma rays. This wasn't from a nearby supernova. It originated from a magnetar located 50,000 light-years away on the far side of our Milky Way galaxy. For a tenth of a second, this single object released more energy than our Sun has emitted in the last 300,000 years. It was so powerful that it actually compressed Earth's magnetic field and ionized the upper layers of our atmosphere, affecting long-range radio communications. To put that in perspective, an event that happened 50,000 years ago from a distance so vast it's difficult to comprehend was still potent enough to reach out and physically touch our planet. That is the raw, untamed power of a magnetar's magnetic field in action. While magnetars represent the ultimate extreme, we don't have to look 50,000 light-years away to witness the raw power of magnetic fields in action. Our very own Sun provides a spectacular, dynamic, and sometimes dangerous showcase of magnetic force happening right in our cosmic backyard. The Sun is not a placid, constant ball of fire. It is a seething, turbulent sphere of superheated plasma, and its churning interior acts as a massive engine for its complex magnetic personality. Deep within the Sun, the movement of this electrically charged gas generates a magnetic field through a process called the solar dynamo. But unlike the relatively stable field of Earth, the Sun's magnetic field is a tangled, ever-shifting web. This is because different parts of the Sun rotate at different speeds. The equator spins faster than the poles, which constantly stretches, twists, and wraps the magnetic field lines. Over time, these lines become increasingly knotted and strained, storing vast amounts of energy. This building tension leads to the most visible sign of the Sun's magnetic activity, the sunspot cycle. Approximately every 11 years, the Sun's magnetic behavior reaches a peak, a period known as the solar maximum. During this time, the number of sunspots visible on its surface dramatically increases. These sunspots are not blemishes, they are planet-sized portals into the Sun's magnetic heart. They appear darker than their surroundings because they are actually cooler. This is a counterintuitive concept. How can a spot on the Sun be cooler? The answer lies entirely with magnetism. A sunspot is a region where a powerful, concentrated bundle of magnetic field lines erupts through the solar surface. This magnetic bundle is so intense that it acts as a barrier, powerfully inhibiting the upwelling of hot plasma from the Sun's interior through a process called convection. With this heat delivery system stifled, the surface area directly above the magnetic bundle cools down from the Sun's normal surface temperature of around 10,000 degrees Fahrenheit to a cooler 6,500 degrees, making it appear dark in contrast. The sheer scale of these magnetic phenomena is breathtaking. A single, large sunspot group can be many times wider than the entire Earth, a testament to the immense forces at play on our local star. This 11-year cycle of magnetic activity is more than just a light show. It's the build-up and release of pent-up magnetic energy on a colossal scale. When those twisted magnetic field lines on the Sun become too strained, they can suddenly and violently reconfigure themselves in a process we touched on with magnetars, magnetic reconnection. This sudden snapping and relinking of field lines converts that stored magnetic energy into a massive burst of radiation and light, an event we call a solar flare. A single, powerful solar flare can release the energy of millions of hydrogen bombs detonating simultaneously, flooding the solar system with intense X-rays and extreme ultraviolet radiation. But the drama doesn't end there. An even more consequential event often accompanies these flares, a coronal mass ejection, or shimmer. This is when the Sun literally ejects a massive portion of its own atmosphere. A shimmer is a billion-ton cloud of magnetized plasma launched from the Sun's outer layer, the corona, and hurled into interplanetary space at speeds of millions of miles per hour. When these gigantic bubbles of magnetic energy are directed toward Earth, the consequences can be profound. Our planet's magnetic field acts as a shield, deflecting most of the incoming solar particles. But during a particularly strong CME, the impact can compress our magnetic field on the day side and violently stretch the field on the night side, like a rubber band being pulled to its limit. This interaction injects immense energy into Earth's magnetosphere, triggering intense geomagnetic storms. The most immediate and beautiful effect of this is the aurora, the northern and southern lights, as energized particles from the sun spiral down our magnetic field lines and collide with atoms in our upper atmosphere, causing them to glow in spectacular curtains of green, red, and purple. However, the technological impact can be far less picturesque. A severe geomagnetic storm can induce powerful electrical currents in long conductors on Earth, such as power grids and pipelines. The most famous historical example, the Carrington event of 1859, was so powerful that telegraph systems, the advanced technology of the day, failed worldwide, with some operators reporting receiving shocks and even being able to send messages with the batteries disconnected, powered solely by the auroral currents. A storm of that magnitude today would have catastrophic effects, potentially causing widespread and prolonged power blackouts, disrupting satellites that govern global communications and GPS, and crippling financial and transportation networks. So, the sun's dynamic magnetic personality serves as a constant reminder that we live in the extended atmosphere of an active star, one whose invisible magnetic forces are a fundamental part of our existence, capable of creating both stunning beauty and significant disruption. But to truly appreciate this cosmic hierarchy of power, let's put these numbers into a direct and sobering comparison. We've seen what a large solar flare can do, unleashing the equivalent of millions of 100 megaton hydrogen bombs all at once. It's an almost ungraspable amount of energy, capable of bathing entire planets in radiation and threatening our technological infrastructure. Now hold that thought and pivot to the deep cosmos. A single typical giant flare from a magnetar, an event lasting just a tenth of a second, can release more energy than our sun will emit over the course of 100,000 years. Let that timescale sink in. 100,000 years ago, our species, Homo sapiens, was sharing the planet with Neanderthals and just beginning to create sophisticated tools and art. From that distant past until today, our sun has been steadily shining, bathing the entire solar system in its life-giving light, powering photosynthesis and driving our climate. A magnetar can outshine that cumulative, epoch-spanning output in the literal blink of an eye. This isn't just a difference in degree, it's a difference in kind. The sun is a steady nuclear furnace, while a magnetar is a magnetic bomb. The energy source is fundamentally different. The sun's power comes from the slow, steady process of nuclear fusion in its core, where hydrogen atoms are fused into helium. A magnetar's flare, however, draws its unimaginable power directly from the catastrophic release of pent-up magnetic energy. It's the difference between the gradual, controlled burn of a massive log and the instantaneous, shattering detonation of high explosives. This comparison starkly illustrates why magnetars are not merely strong magnetic objects. They are in a league of their own, operating on a scale of magnetic fury where the normal rules of stellar physics no longer apply. They are the universe's ultimate magnetic reservoirs, capable of channeling the energy of 100 millennia into a flash of light that can be seen clear across the galaxy. Now, let's meet the more orderly and predictable cousins of the chaotic magnetars, the pulsars. Both are born from the same cataclysmic supernova explosions. Both are city-sized neutron stars of unimaginable density, but they express their power in a fundamentally different way. While a magnetar is defined by the sheer, raw strength of its magnetic field, a pulsar is characterized by its incredible metronomic spin and the precision of its emissions. Imagine a cosmic ballerina spinning at a dizzying rate after a star's dramatic death. As the core of the progenitor star collapses, a fundamental principle of physics called the conservation of angular momentum takes over. Much like an ice skater pulling their arms in to spin faster, the collapsing star's core, which was already rotating, speeds up tremendously. The result is a neutron star that can complete dozens, hundreds, or even over 700 full rotations every single second. That means the entire mass of our Sun, compressed into a 12-mile-wide sphere, is spinning so fast that its surface is moving at a significant fraction of the speed of light. This rapid rotation is the engine for one of the most iconic phenomena in all of astronomy, the pulsar's lighthouse effect. The pulsar's immensely powerful magnetic field, which is still about 1 trillion times stronger than Earth's, a force that would easily vaporize any spacecraft, is not perfectly aligned with its axis of rotation. Instead, the magnetic poles are offset. Charged particles become trapped and accelerated along the intense field lines near these magnetic poles, producing powerful beams of radiation that shoot out from the north and south magnetic regions. These are not gentle glows, they are focused cones of intense radio waves, X-rays, or even gamma rays, much like the focused beam from a lighthouse. And as the pulsar spins, these beams sweep through space like a cosmic searchlight. If you happen to be located in the path of one of those sweeping beams, you will detect a fantastically regular pulse of energy with each rotation. From our perspective on Earth, it looks as though the object itself is turning on and off with a rhythm so precise it rivals the best atomic clocks we can build. The discovery of the first pulsar in 1967 by Jocelyn Bell Burnell was so startlingly regular that the source was initially half-jokingly nicknamed LGM-1 for Little Green Men, as the team seriously considered the possibility they had found a beacon from an extraterrestrial civilization. We now know these are natural phenomena, but their precision is no less astounding. This clockwork nature makes pulsars incredible tools for scientists. They serve as celestial navigation beacons, potential tools for detecting gravitational waves, and natural laboratories for testing the laws of physics under extreme gravity. So, while they may not possess the magnetic fury of a magnetar, pulsars command their own form of respect, using rhythm and precision to broadcast their existence across the galaxy. This incredible interplay between rapid spin and magnetic fury finds one of its most breathtaking expressions not in isolation, but in the magnificent cosmic sculpture it helps to create. We often admire nebulae, those vast, colorful clouds of gas and dust in space, as beautiful cosmic artworks, but what shapes these ethereal forms? The answer, in many cases, is the invisible hand of magnetism. A spectacular example of this is the Crab Nebula, the expanding remnant of a supernova that was so brilliant it was recorded by Chinese and Arab astronomers in the year 1054 AD. At the heart of this swirling, 6-light-year-wide cloud of debris lies the crushed core of the star that exploded, a pulsar. This particular pulsar is a dynamo, spinning 30 times every second and blasting out a relentless wind of high-energy particles and, crucially, a powerful magnetic field. Imagine this pulsar as a cosmic hurricane with the nebula around it as the storm-tossed sea. The pulsar wind, carrying this embedded magnetic field, slams into the slower-moving expanding shell of gas from the ancient explosion. This interaction does more than just light up the gas, it organizes it. The magnetic field acts like a scaffold or an invisible framework, channeling the chaotic energy and giving structure to the chaos. It helps to confine the superhot gas into the intricate filamentary tendrils that make the Crab Nebula so iconic in telescope images. These filaments aren't just random wisps, they are patterns etched by magnetic force, with the field lines guiding the flow of charged particles and preventing the nebula from simply dissipating into a formless haze. Furthermore, we can see the direct influence of the pulsar's spin axis in the form of powerful jets shooting out from its poles, carving through the nebula material. The entire system acts like a giant neon sign, powered by the pulsar's rotational energy and shaped by its magnetic will. This demonstrates a profound cosmic truth. Magnetic fields are not just destructive forces, they are the master sculptors of the interstellar medium. They mold the clouds where new stars are born, they give structure to the remnants of dead stars, and they transform violent stellar death into some of the most enduring and beautiful structures in our galaxy. But to truly grasp the pervasive influence of magnetic fields, we need to pull our perspective all the way back from the violent deaths of stars to the grand architecture of our home galaxy. It might come as a surprise, but the entire Milky Way is magnetized. Our galaxy is threaded by a vast, invisible web, a galactic magnetic field. This isn't a single, simple bar magnet on a cosmic scale. It's a complex, turbulent, and filamentary structure woven through the very fabric of the space between the stars, a part of what we call the interstellar medium. This galactic field is incredibly diffuse and weak by the standards we've been discussing, trillions of times weaker than a magnetar's field, and even 1,000,000 times weaker than Earth's protective magnetic bubble. Yet, its sheer scale makes it a dominant force in shaping the ecology of our galaxy. This field didn't appear by magic, it was generated and is continuously amplified by the motion of charged particles within the galactic disk. As stars are born and die, they churn the interstellar medium with their winds and explosions, and the slow, differential rotation of the galaxy itself stretches and twists these magnetic field lines, creating a dynamic and messy cosmic tapestry. One of the most critical roles this galactic field plays is as a regulator for some of the universe's most energetic travelers, cosmic rays. These are not rays of light, but high-speed atomic nuclei, mostly protons, racing through space at nearly the speed of light. They originate from supernova remnants and other violent sources, and if they traveled in straight lines, they would be incredibly difficult to track and would pose a far greater radiation hazard to worlds like ours. The Milky Way's magnetic field acts as a giant, chaotic maze. It doesn't stop cosmic rays, but it does something just as important: it deflects them. The charged particles spiral along the invisible magnetic field lines, bouncing and twisting their way through the galaxy. This process effectively traps them within the galactic disk for millions of years, turning them into a trapped, high-energy population that fills the galaxy. This magnetic maze is also a fundamental sculptor of star birth. Stars form when vast clouds of gas and dust, called molecular clouds, collapse under their own gravity. But gravity isn't the only force at play. These clouds are threaded with magnetic fields, and these fields exert a pressure that pushes back against gravity's relentless pull. This magnetic support can significantly slow down the collapse of a cloud, acting as a cosmic timer that controls the rate of star formation. In some cases, the field can even channel the flow of gas, guiding it into specific streams and filaments that determine where and how many new stars will eventually ignite. It's a delicate balancing act between the inward crush of gravity and the outward push of magnetism, a dance that dictates the future stellar population of the galaxy. So, how do we map something as invisible and wispy as a galaxy-wide magnetic field? We use a clever trick of nature involving starlight and cosmic dust. The space between stars is filled with tiny, elongated dust grains. As starlight travels through these dusty regions, these grains tend to align themselves with the direction of the galactic magnetic field, much like countless tiny compass needles. When light encounters these aligned grains, it becomes polarized, meaning its light waves oscillate in a preferred direction perpendicular to the field. By analyzing the polarization of starlight from thousands upon thousands of stars across the galaxy, astronomers can essentially trace the orientation of the magnetic field lines that the light passed through. This allows us to create a rough map of our galaxy's magnetic skeleton, revealing the grand, invisible currents that structure the cosmos on the very largest scales. While we've seen how magnetism sculpts the grand structures of galaxies and the remnants of dead stars, its influence is just as profound at the very beginning of a star's life, in the cosmic nurseries where planets are born. To understand this, let's journey to a familiar sight in astronomy, a dark, cold nebula of gas and dust like the Orion Nebula. Within these clouds, pockets of material collapse under gravity, but they don't simply fall straight in. Because of the tiny amount of rotation inherent in the cloud, the collapsing material flattens into a vast, spinning disk encircling the newborn protostar. This is a protoplanetary disk, a frenetic construction zone where the star is finishing its assembly and the raw materials for planets are coming together. Now, this disk faces a fundamental physics problem. The material closest to the young star is whipping around it very quickly, while the outer material moves more slowly, much like the different orbital speeds of planets in our solar system. For the star to grow, gas and dust from the inner disk need to spiral inward and accrete onto its surface. But there's a conservation law in physics, the conservation of angular momentum, that acts like a barrier. Think of a figure skater spinning. As they pull their arms in, they spin faster. If the disk material simply moved inward, it would have to spin impossibly fast. Something must act as a brake, removing that rotational energy and angular momentum from the inner disk and transferring it outward, so the material can slow down enough to fall onto the star. This is where magnetic fields become the master choreographers of the disk. The protoplanetary disk is not a passive, neutral gas. It's a weakly ionized plasma filled with charged particles. As the disk rotates, these charged particles interact with any ambient magnetic field, and the differential rotation, the inner part moving faster than the outer part, winds up the magnetic field lines. They become stretched and twisted like elastic bands being wound tighter and tighter. This winding creates a powerful magnetic tension, and this tension exerts a torque on the disk material. This process, known as magnetorotational instability, is incredibly effective. It acts as a cosmic conveyor belt for angular momentum, systematically moving it from the inner, fast-spinning regions to the outer, slower regions. This allows the inner disk material to lose its rotational energy and finally succumb to gravity, spiraling in to feed the growing star. Without this magnetic mechanism, the accretion process might stall, leaving the star starved for fuel and drastically altering the entire timeline of stellar and planetary formation. But the magnetic field's job in this nursery is far from over. It also has a direct hand in building the planets themselves. In the early stages, microscopic dust grains are all that exist. For planets to form, these tiny specks must first stick together to form larger and larger bodies, eventually growing into planetesimals, the kilometer-sized building blocks of planets. Magnetic fields can significantly influence this delicate dance. Dust grains themselves can become electrically charged within the disk environment. If a magnetic field is present, these charged grains no longer move solely under gravity. Their motion is also governed by the magnetic forces. This can either help or hinder their growth. In some scenarios, the magnetic field can help concentrate these grains in specific regions, increasing their collision rate and helping them clump together faster. In others, it might stir up the dust, preventing the calm settling needed for the gentle collisions that lead to sticking. It's a complex, dynamic interplay that scientists are still actively working to understand, but it's clear that the local magnetic environment is a key player in determining whether a disk will efficiently produce rocky worlds like Earth or remain a barren swirl of dust. Perhaps the most visually spectacular role of magnetism occurs right at the surface of the young star itself. These infant suns possess incredibly strong magnetic fields, often thousands of times more powerful than our sun's current field. As material from the disk finally spirals all the way in, it doesn't fall evenly onto the star's surface. Instead, it is captured and funneled by the star's powerful magnetic field lines. The material, now a superheated plasma, is forced to flow along these invisible tracks, streaming down from the inner edge of the disk directly onto the star's magnetic poles. These focused streams are called accretion columns. Imagine two powerful, luminous tornadoes of million-degree gas, each the width of a continent, screaming down from space and impacting the stellar surface at the poles. The energy released at the base of these columns is staggering, creating intensely hot spots that glow brilliantly in X-rays and ultraviolet light. This violent, magnetically guided accretion is a defining characteristic of a young stellar object's life, a dramatic and energetic phase that shapes the star's early evolution and bathes the entire fledgling planetary system in a harsh, ionizing radiation that itself influences the chemistry of the emerging planets. So, from orchestrating the flow of an entire disk to guiding the final plunge of material onto the star, magnetic fields are the invisible architects without which the orderly construction of solar systems like our own might never begin. Returning from the galactic scale to our own cosmic neighborhood, we find a planetary magnetic powerhouse that dwarfs all others, a giant whose influence dominates the space around it. The undisputed champion of planetary magnetism in our solar system is Jupiter. This colossal gas giant, large enough to contain over 1,300 Earths, boasts a magnetic field that is equally immense, approximately 20,000 times stronger than the protective bubble surrounding our own planet. To understand the source of this phenomenal power, we have to journey deep into Jupiter's alien interior, a place where matter exists in a state we can never replicate on Earth. Unlike our world with a core of molten iron, Jupiter's engine room is fueled by an ocean of metallic hydrogen. Under the crushing pressures found deep within the planet millions of times the pressure of Earth's atmosphere, hydrogen, the simplest and most abundant element, undergoes a breathtaking transformation. Its atoms are squeezed so tightly that their electrons are liberated, turning the normally gaseous element into a liquid metal. This metallic hydrogen is a phenomenal electrical conductor, and it's this vast, swirling, conductive ocean that acts as the dynamo. Jupiter's incredibly rapid spin acts as the motor for this dynamo. Despite its enormous size, the planet completes a full rotation in just under 10 hours. This furious spin, combined with the churning convection currents within the metallic hydrogen layer, generates electrical currents on a planetary scale, which in turn produce that staggering magnetic field. The sheer reach of this magnetic influence is almost beyond comprehension. Jupiter's magnetic domain, its magnetosphere, is the largest permanent structure in our solar system. If our eyes could perceive magnetic fields, the magnetosphere of Jupiter would appear larger than the full moon in our night sky, even from over 400 million miles away. This vast, invisible bubble doesn't just sit there, it actively shapes its environment. As the solar wind, that constant stream of charged particles from the sun flows outward, it slams into Jupiter's magnetic field. The solar wind is forced to part and flow around this immense obstacle, compressing the field on the sunward side and stretching it into an enormous, comet-like tail that extends all the way to the orbit of Saturn, over 400 million miles in the opposite direction. Within this gargantuan magnetic cavity, Jupiter traps and accelerates charged particles, creating radiation belts of unimaginable intensity. These belts, similar to Earth's Van Allen belts but billions of times more powerful, are filled with electrons, protons, and other ions whirling at nearly the speed of light. The radiation here is so fierce it will be instantly lethal to any unprotected spacecraft or astronaut, and it even affects Jupiter's innermost moons, bathing their surfaces in a continuous, energetic hail that alters their surface chemistry and poses a significant challenge for future exploration. This magnetosphere is not a static shield. It's a dynamic, roaring arena of magnetic storms and powerful auroras that dwarf their earthly counterparts, making Jupiter a constant, vibrant laboratory for the study of extreme planetary magnetism. These breathtaking celestial curtains of light are far more than just a beautiful spectacle. They are the most visible and dramatic signature of a planet's magnetic field in action. The process begins 93 million miles away with our Sun. The solar wind, a constant stream of charged particles, mostly electrons and protons, flows outward from the Sun at speeds of over 1 million miles per hour. When this invisible river of energy reaches Earth, it meets our planet's global magnetic field, our magnetosphere. For the most part, this field acts as a protective shield, deflecting the bulk of the solar wind around our planet like a rock diverting a stream of water. But our magnetic shield is not a perfect, impenetrable barrier. Some of these high-energy particles manage to become trapped within the magnetosphere, and here's where the magic happens. The configuration of Earth's magnetic field, with its lines converging at the north and south magnetic poles, acts like a gigantic funnel. These trapped particles are guided along the invisible magnetic field lines, spiraling down toward the polar regions. As they plunge into the upper atmosphere, roughly 60 to several hundred miles above the ground, they collide with atoms and molecules of oxygen and nitrogen. These collisions are incredibly energetic. The incoming solar wind particle transfers its energy to the atmospheric atom, boosting one of its electrons into a higher energy level or an excited state. But an atom doesn't like to stay in this energized condition for long. Almost instantly, the electron drops back down to its normal state, releasing that excess energy in the form of a tiny packet of light, a photon. When you see the shimmering green of an aurora, you are witnessing countless trillions of oxygen atoms high in the atmosphere, releasing this specific shade of green light as they relax from their excited state. Red auroras come from high-altitude oxygen, while blue and purple hues are typically emitted by nitrogen molecules. It's a planet-scale chemical light show powered by the Sun and orchestrated entirely by Earth's magnetic field. But if our aurorae are a stunning display, the versions found on the gas giants are on an entirely different scale of grandeur. Jupiter, with its magnetic field 20,000 times stronger than Earth's, hosts the most powerful auroral displays in the entire solar system. These are not fleeting, solar wind-dependent events. They are permanent, roaring rings of light encircling the planet's poles. While the solar wind does contribute, Jupiter's aurorae have an additional, incredible power source, its own moon, Io. Io is the most volcanically active body in the solar system, its surface tormented by constant eruptions that spew vast amounts of sulfur dioxide gas into space. This material becomes ionized, creating a giant, donut-shaped cloud of charged particles that follows Io in its orbit around Jupiter. Jupiter's immense magnetic field sweeps through this cloud, stripping away the charged particles and channeling them along magnetic field lines toward the planet's poles. This creates a constant, torrential downpour of energetic particles onto Jupiter's upper atmosphere, generating aurorae that are hundreds of times more energetic than Earth's. These aurorae are not just visible in familiar colors, they glow fiercely in ultraviolet and even X-ray wavelengths, releasing more total energy than all the electrical power generated by humanity in its entire history. Saturn, too, boasts its own spectacular permanent auroral ovals, driven by a similar combination of solar wind and particles from its icy, geyser-spewing moon, Enceladus. These planet-sized light shows are a brilliant demonstration that the beautiful physics of aurorae is a universal phenomenon, one whose intensity is a direct reflection of the sheer magnetic might of the world it adorns, while Jupiter showcases planetary magnetic power through its immense size and metallic hydrogen core. A journey to the outer solar system reveals magnetic fields that are not just powerful but profoundly strange. The ice giants Uranus and Neptune are the solar system's eccentrics, harboring magnetic fields that defy the standard rules of planetary behavior. Unlike the relatively tidy dipole fields of Earth, Jupiter, and Saturn, which resemble the field of a simple bar magnet roughly aligned with the planet's spin, the magnetic fields of Uranus and Neptune are chaotic, lopsided, and dramatically askew. Imagine a planet where the magnetic North Pole isn't located anywhere near the geographic North Pole. In fact, on Uranus, the entire magnetic field is offset from the planet's center by a staggering distance, nearly 60% of the planet's radius, and tilted at a wild 59-degree angle from its axis of rotation. This means the magnetic field doesn't wrap symmetrically around the planet but emerges from a region far off to the side, creating a magnetic environment that is fundamentally unbalanced and complex. Neptune exhibits a similarly bizarre configuration, with a field that is both tilted and substantially offset. This bizarre geometry points to a completely different kind of magnetic engine humming deep within these frozen worlds. Planetary scientists believe the key lies not in a core of molten metal, but in a unique and exotic state of matter. Deep within Uranus and Neptune, the immense pressures and temperatures create a vast, hot, and dense ocean. But this isn't an ocean of water as we know it. It's a supercritical fluid of water, ammonia, and methane ices that, under these extreme conditions, becomes electrically conductive. This is the proposed dynamo region. Unlike the deep, planet-spanning metallic hydrogen layers of Jupiter, this conductive ocean on the ice giants is thought to be a relatively thin, shell-like layer, confined to a specific depth range above a rocky core. It's within this churning, electrically conductive slush that the planetary magnetic field is generated. The dynamo process here is inherently more complex and constrained, likely leading to the multiple, off-center, and severely tilted fields that the Voyager 2 spacecraft measured during its fleeting flybys. This strange internal structure makes these distant worlds natural laboratories for studying magnetic dynamos under conditions we cannot recreate on Earth, revealing that the universe has more than one recipe for building a planetary magnet. Moving from the staggering magnetic displays of gas giants back to our own world, we find a field that, while far weaker in raw power, is perfectly tuned for one critical purpose: sustaining life. Earth's magnetic field is our planet's silent, invisible guardian, a global force field that we largely take for granted, yet it is arguably the single most important feature that makes our world a living one. This magnetosphere extends tens of thousands of miles into space, creating a protective bubble that envelops our entire planet. Its primary job is to stand against the relentless stream of charged particles constantly flowing from the sun, the solar wind. When this supersonic plasma reaches Earth, it doesn't hit our atmosphere head-on. Instead, it encounters our magnetic field, which acts like a skilled martial artist, deflecting the vast majority of these energetic particles around the planet. They slide and spiral along the outside of the magnetosphere in a region called the bow shock, harmlessly diverted into the void. This deflection is not just a minor interaction. It is the fundamental reason Earth still has a thick, life-sustaining atmosphere. Without this magnetic shield, the solar wind would have direct, unimpeded access to our upper atmosphere. Over millions of years, the constant bombardment would have literally sandblasted our air away, molecule by molecule, stripping it into space. We have a stark, nearby example of this tragic fate: Mars. The red planet is a cold, arid desert today largely because it lost its global magnetic field billions of years ago. With no planetary shield to protect it, the solar wind was free to systematically erode what was once a much thicker atmosphere, turning a potentially habitable world into the barren landscape we see today. Earth's magnetic field effectively prevents this atmospheric stripping, holding our life-giving blanket of nitrogen and oxygen securely in place. This protective role extends directly to the safety of life on the surface. Beyond the solar wind, the universe is filled with far more energetic and dangerous particles known as cosmic rays. These are atomic nuclei accelerated to nearly the speed of light by distant supernova and other cataclysmic events. When these high-energy cosmic rays enter our atmosphere, they collide with air molecules, creating a cascade of secondary particles. Our planet's magnetic field acts as the first line of defense, bending the paths of many of these incoming cosmic rays and the most energetic particles from solar storms, forcing them toward the poles or trapping them in the Van Allen radiation belt. This drastically reduces the amount of harmful radiation that reaches the surface, shielding living organisms from genetic damage and reducing the risk of mutations and cancers. For any potential future long-duration space travelers, this protection is something they would keenly miss. Outside the comforting embrace of the magnetosphere, radiation exposure becomes one of the most significant hazards. So, while we may marvel at the magnetic titans of the cosmos, it is our own world's perfectly calibrated, steadfast magnetic field that provides the safe harbor necessary for the complex and delicate chemistry of life to not just begin, but to thrive and evolve over billions of years. It is the ultimate planetary life support system, an invisible bulwark against the harsh realities of space. But this vital protective shield that has allowed life to flourish on Earth is far from a permanent, unchanging fixture. It has a dramatic and unpredictable history of its own. The solid ground beneath our feet feels constant and reliable, yet the invisible magnetic field enveloping our planet is in a state of constant dynamic flux. One of the most profound facts about our planetary guardian is that it has repeatedly reversed its polarity throughout Earth's long history. The magnetic north and south poles have completely swapped places not just once but hundreds of times. This isn't a rapid flick of a switch event. The process is gradual, occurring over thousands of years. The evidence for these dramatic flip-flops is literally set in stone. When volcanic lava erupts and cools, tiny, iron-rich minerals within the rock, like magnetite, act like countless microscopic compass needles. As the rock solidifies, these minerals lock into place, aligning themselves perfectly with the direction and inclination of Earth's magnetic field at that exact moment in geological time. This creates a permanent, unchangeable record of the field's orientation, frozen in time for millions of years. Geologists can drill into ancient lava flows around the world, and by measuring the magnetic direction in these rocks, construct a timeline of our planet's magnetic past. Even more compelling evidence comes from the deep ocean floor. As new crust is formed at mid-ocean ridges, magma wells up and cools, and its magnetic minerals similarly record the field's polarity. As the seafloor slowly spreads away from the ridge over millions of years, it creates a symmetrical, striped pattern on either side of the ridge, a veritable barcode of magnetic reversals, with dark stripes representing periods of normal polarity, like today, and light stripes representing periods of reversed polarity. This discovery in the 1960s was one of the key pieces of evidence that proved the theory of plate tectonics, showing that the seafloor was indeed spreading and that our planet's magnetic field was a dynamic global storyteller. These geological archives reveal that reversals are not periodic, they are chaotic. The time between flips is wildly irregular, ranging from as little as tens of thousands of years to tens of millions of years. On average, a reversal happens roughly every 200 to 300,000 years. Intriguingly, our current period of stable polarity, known as the Bruns normalchron, has already lasted about 780,000 years, meaning that, statistically speaking, we are long overdue for a flip. So, what actually happens during one of these monumental events? The process begins deep within the Earth's outer core, where the turbulent flow of molten iron generates our magnetic field through the dynamo effect. Computer simulations suggest that reversals likely start when the flow patterns in the core become sufficiently chaotic to disrupt and overwhelm the main dipole field. The orderly two-pole structure begins to break down. The field doesn't just smoothly rotate, it becomes a complex, multipolar mess. Multiple, weaker magnetic north and south poles can pop up in strange places all over the globe. During this transitional period, which can last from 1,000 to 10,000 years, the overall strength of Earth's magnetic field plummets, potentially to as little as 10% of its normal power. This is the most significant consequence of a magnetic reversal. a weakened magnetic field is a less effective shield. With our planet's primary defense system compromised, higher levels of solar and cosmic radiation would be able to penetrate much deeper into our atmosphere. This wouldn't be an extinction-level event for life on the surface. The atmosphere itself is still a very effective radiation shield, but it would pose substantial challenges. The increased radiation at high altitudes could be a genuine hazard for astronauts and could damage or destroy the sensitive electronics aboard low-orbiting satellites that we rely on for communication, weather forecasting, and GPS. Furthermore, a complex multipolar field would play havoc with navigation for the many species, from sea turtles and birds to bacteria, that are known to use the Earth's magnetic field for migration and orientation. The scientific quest to understand and predict these reversals is one of the great challenges in geophysics. Researchers use sophisticated satellite missions, like the European Space Agency's Swarm constellation, to create highly detailed maps of the current magnetic field and monitor its rapid changes. They have identified specific regions where the field is behaving unusually, most notably a large area over the South Atlantic Ocean where the field is significantly weaker, a feature known as the South Atlantic Anomaly. This is already a region where satellites experience increased radiation and technical glitches. Some scientists speculate this could be the birthplace of the next reversal. By combining these precise satellite measurements with advanced computer models that simulate the complex fluid dynamics of the Earth's core, researchers hope to one day be able to forecast a reversal, much like we forecast weather. While the idea of the poles flipping might sound like a doomsday scenario, it's important to remember that life on Earth has persisted through hundreds of these events. The geological record shows no correlation between mass extinctions and magnetic reversals. For humanity, the greatest impact would be on our technology-dependent society, forcing us to develop more radiation-hardened systems and adapt our infrastructure. The ongoing dance of the Earth's core ensures that our protective magnetic shield is a living, breathing entity, and its next great transformation is not a matter of if but when. But our exploration of magnetic stellar remnants doesn't end with the incredible density of neutron stars. There exists another, more common afterlife for stars like our own Sun, a fate that can also host surprisingly powerful magnetic fields. These are the white dwarfs. When a star of low to medium mass nears the end of its life, it doesn't explode in a supernova. Instead, it gently puffs off its outer layers, creating a beautiful planetary nebula, while the star's hot, exposed core is left behind. This core, no longer supported by nuclear fusion, collapses under its own gravity until it is compressed into an object roughly the size of Earth, but with a mass comparable to our Sun. This is a white dwarf, a sphere of degenerate matter where the pressure of densely packed electrons prevents further gravitational collapse. It's the final, fading ember of a star's life. Now, within this population of stellar embers, astronomers have discovered a fascinating subgroup, the magnetic white dwarfs. These objects possess magnetic fields that, while not reaching the universe-shattering intensities of magnetars, are still phenomenally powerful by any other standard. Their fields can measure up to 100,000 times stronger than Earth's, and in the most extreme cases can even approach 1 billion Gauss. To put that into perspective, that's about 1,000 times stronger than a typical sunspot's magnetic field. The origin of these intense fields is a topic of active research, but the leading theory points to a fascinating concept, the fossil field hypothesis. Imagine the magnetic field that was woven throughout the entire star during its active main sequence life. When the star goes through its death throes, shedding its outer layers, that original global magnetic field doesn't just vanish. Instead, as the core collapses down to form the white dwarf, the magnetic flux, the total number of magnetic field lines is largely conserved. It's the same principle of magnetic flux conservation we saw with neutron stars, just on a less extreme scale. If you take a magnetic field spread throughout a sphere the size of the Sun and compress that sphere down to the size of Earth, the field lines are forced much closer together, dramatically amplifying the field's strength at the surface. This preserved or fossil field is a relic from the star's earlier existence, a magnetic memory frozen into the white dwarf for the rest of its long life. The presence of such a powerful field has profound effects on how we observe these objects. One of the most telling signatures is the polarization of their light. As light travels through a magnetized medium, the magnetic field can cause the light waves to oscillate in a preferred direction, a phenomenon known as polarization. For a strongly magnetic white dwarf, the light emitted from its entire surface becomes strongly polarized. When astronomers analyze this light with special instruments, they don't see a smooth spectrum. They see one that is split and shifted in a distinctive pattern called Zeeman splitting, where individual spectral lines are divided into multiple components by the magnetic field's influence. It's as if the magnetic field is stamping a unique, identifiable barcode onto the star's light, allowing us to measure its strength and structure from vast distances. Furthermore, if the white dwarf is in a binary system with a companion star, its magnetic field becomes the absolute master of any material transfer. In a non-magnetic system, gas flowing from a companion star would form a tidy, spinning disk around the white dwarf before gradually spiraling onto its surface. But when a powerful magnetic field is present, this orderly process is completely overthrown. The field acts as a giant gatekeeper, disrupting the formation of an accretion disk entirely. Instead, the incoming gas is captured by the magnetic field lines far from the star and funneled directly onto the white dwarf's magnetic poles, much like the accretion columns on a young protostar. This creates incredibly hot spots at the poles, which rotate in and out of our view as the star spins, causing the white dwarf's brightness to pulse with a regular rhythm. These pulsations provide astronomers with another clear fingerprint for identifying these magnetic powerhouses. So, while they may be less dense and less violent than their neutron star cousins, magnetic white dwarfs stand as crucial testament to the enduring legacy of stellar magnetism, proving that even in a star's final, fading days, magnetic fields can remain a dominant and defining force. Now, let's turn our attention to one of the most spectacular and violent events in the cosmos, the supernova, and discover how invisible magnetic fields are often the hidden architects directing the chaos. When a massive star reaches the end of its life and its core collapses, the resulting explosion is not always a perfectly symmetrical blast. For a special class of these stellar detonations, the sheer force and structure of the star's magnetic field become the decisive factor, transforming a standard supernova into something far more extreme and focused. In a typical core collapse supernova, the star's iron core, no longer supported by nuclear fusion, implodes under its own immense gravity, rebounding in a shock wave that blows the star apart. But when the progenitor star is spinning very rapidly and possesses an intensely powerful magnetic field, that energy doesn't just expand outward in a sphere. Instead, the dynamics change completely. The star's interior, in its final moments, resembles a colossal natural engine. The infalling material from the outer layers of the star swirls down toward the rapidly spinning core, winding the embedded magnetic field lines tighter and tighter, like twisting a rubber band to its absolute limit. This process amplifies the magnetic field to phenomenal strength, billions of times stronger than the Sun's field, creating an immense magnetic pressure that fights back against the inward crush of gravity. This magnetic pressure can't escape equally in all directions. It finds the path of least resistance along the star's rotational axis, where the centrifugal force is weakest. The result is that the magnetic field acts like a pair of unimaginably powerful cosmic slingshots, channeling the outgoing shock wave and a torrent of stellar material into two narrow, opposing jets that blast outward at velocities approaching the speed of light. This focused, jet-driven explosion is what astronomers classify as a hypernova, a supernova that can be up to 100 times more energetic than a standard supernova. It is this very mechanism where magnetism dictates the direction of the blast that is also the leading explanation for the origin of long-duration gamma-ray bursts. These are the most luminous electromagnetic events known to occur in the universe, fleeting flashes of gamma rays that can outshine entire galaxies for a minute or two. A long gamma-ray burst is essentially the birth cry of a hypernova, seen from a very specific angle. If our line of sight happens to be looking right down the barrel of one of these ultra-relativistic jets, we are treated to the full, focused fury of the event, a concentrated beam of the highest energy radiation the universe can produce. The magnetic field does more than just collimate the jet. It also acts as a powerful particle accelerator within the jet itself, further energizing the material and helping to produce that brilliant flash of gamma rays. So, when we witness the awesome power of a gamma-ray burst lighting up the distant cosmos, we are not just seeing a star dying. We are seeing the final, spectacular testament to the power of its magnetic field, a force capable of taking a spherical catastrophe and focusing it into a pair of cosmic blowtorches that can be seen clear across the observable universe. Yet for all the staggering power of magnetic fields from planets to pulsars, there is a profound and elegant symmetry missing from our understanding of magnetism itself. We are surrounded by electric charges. You can have a solitary positive proton or a negative electron. These are electric monopoles, but if you take a simple bar magnet and break it in half, you don't end up with an isolated north pole and an isolated south pole. Instead, you create two smaller magnets, each with its own north and south. No matter how many times you split it, you can never isolate a single magnetic pole. This fundamental difference is one of the most tantalizing puzzles in physics, leading to the theoretical hunt for a particle that has never been found, the magnetic monopole. Its existence was first seriously proposed by physicist Paul Dirac in 1931, who showed that if even one magnetic monopole existed somewhere in the universe, it would beautifully explain a fundamental mystery: why electric charge comes in discrete quantized units. The math was compelling, suggesting that magnetism and electricity could be united in a more symmetric and complete theory. The search then shifted to the earliest moments of creation. Cosmologists theorize that in the unimaginably hot, dense energy of the Big Bang, during a phase transition as the universe rapidly expanded and cooled, topological defects in the fabric of spacetime could have condensed into massive, stable particles carrying a net magnetic charge. These would not be tiny particles like electrons. They would be super-heavy, primordial relics, potentially as massive as a bacterium yet smaller than an atom, carrying a magnetic charge billions of times stronger than the poles of a subatomic particle. Finding just one of these cosmic unicorns would be a discovery on par with the Higgs boson, instantly rewriting textbooks and confirming grand unified theories that attempt to merge the electromagnetic force with the strong and weak nuclear forces. It would prove that the universe treats electricity and magnetism with perfect, symmetric respect. The hunt for magnetic monopoles has been one of the most extensive and creative searches in modern science. Physicists have looked everywhere. They have examined ancient crystals of mica, searching for telltale scars that a heavy, charged monopole would have left as it plowed through the mineral over millions of years. They have built sophisticated detectors in deep underground labs, hoping to catch the unique, high-energy signature of a monopole passing through. Experiments have been conducted using samples from the deep ocean floor and cores drilled from the pristine ice of Antarctica. Massive particle accelerators like the Large Hadron Collider have repeatedly attempted to create these elusive particles by smashing protons together at nearly the speed of light, replicating the energy conditions of the early universe. The most famous dedicated experiment was conducted by physicist Blas Cabrera in 1982, who recorded a single event in his ultra-sensitive superconducting loop that perfectly matched the predicted signal of a magnetic monopole. The scientific community held its breath, but the signal was never seen again, leaving the result as an unexplained and tantalizing anomaly. The continued, utter absence of any confirmed monopole poses a significant challenge to our theories. Their non-discovery is, in itself, a profound piece of data, forcing physicists to refine their models of cosmic inflation and the fundamental symmetries of nature. It remains one of the most captivating open cases in physics, a ghost particle whose existence is demanded by beautiful mathematics, yet whose presence continues to elude us, a fundamental piece of the cosmic puzzle that is still missing. Measuring these invisible titans across the vast emptiness of space is one of astronomy's greatest challenges, but scientists have developed some remarkably clever techniques to reveal the strength and structure of these hidden forces. One of the most fundamental and direct methods relies on a phenomenon known as the Zeeman effect. To understand how this works, picture an atom as a tiny transmitter, emitting light at very specific colors or frequencies that act like its unique fingerprint. Now imagine placing that atom within a powerful magnetic field. The field interacts with the electrons in the atom, causing this fingerprint to change in a distinctive way. The single, sharp spectral line we would normally see splits into two or more components, each polarized in a different direction. It's as if the magnetic field is gently pulling the atom's light signature apart. The beauty of this effect is that the amount of splitting is directly proportional to the strength of the magnetic field causing it. By carefully analyzing starlight with powerful spectrographs, astronomers can look for this telltale splitting in the light from the surfaces of stars or within swirling clouds of interstellar gas. When they detect it, they can perform a straightforward calculation to determine the precise strength of the magnetic field at that location, turning an invisible force into a number we can measure from light years away. This technique is particularly powerful for studying the intense magnetic fields on stars like sunspots or the surfaces of magnetic white dwarfs, where the splitting of spectral lines provides a clear and quantifiable readout of the magnetic power at work. While the Zeeman effect reveals field strength, another elegant method maps out the field's orientation across immense stretches of space using an effect that relies on cosmic dust. The void between stars is not completely empty. It is sprinkled with tiny, elongated dust grains made of silicate and carbon. These minuscule grains act like countless miniature compass needles. When a magnetic field permeates a region of space, these dust grains tend to align themselves with the direction of the field lines. It's a subtle process, but it has a dramatic effect on any starlight that passes through that dusty, magnetized region. As the light travels through, the aligned dust grains preferentially absorb and scatter light vibrating in one particular direction, making the starlight that emerges become polarized. This means the light waves oscillate in a preferred plane rather than randomly. When astronomers on Earth capture this light and analyze its polarization, they can directly trace the orientation of the magnetic field that the light encountered on its long journey. By measuring the polarization from thousands of stars across a specific cloud or even an entire galaxy, they can piece together a grand map of the magnetic field structure, revealing its sweeping arcs and turbulent twists. This is how we know the large-scale magnetic skeleton of our own Milky Way, charting the invisible pathways that guide cosmic rays and influence the birth of new stars. For the most dramatic and energetic magnetic environments, astronomers turn to a third spectacular signature, synchrotron radiation. This is the light produced by the ultimate cosmic roller coaster. When electrons are accelerated to velocities approaching the speed of light and are then forced to spiral along magnetic field lines, they don't just move, they radiate. The process is akin to whirling a glowing sparkler in a dark circle. You see a continuous trail of light, In space, these ultra-relativistic electrons, often accelerated by supernova shockwaves or within the jets of active galaxies, emit a brilliant, distinctive glow as they corkscrew through magnetic fields. This synchrotron radiation has a unique character. It is polarized and shines most brightly at radio wavelengths, often with a characteristic harsh, bluish tint in visible light images. Whenever you see the intricate, filamentary glow of a supernova remnant like the Crab Nebula, you are looking at synchrotron radiation in action. The eerie, bluish light in the nebula's center isn't coming from hot gas in the traditional sense. It is the direct emission from electrons spiraling at near light speed through the pulsar's intense magnetic field. This powerful tracer allows scientists to not only locate regions of strong magnetic fields and particle acceleration, but also to estimate the energy of the particles and the strength of the fields themselves, painting a dynamic picture of cosmic powerhouses where magnetic forces are hard at work. Now, let's take this magnetic choreography to the ultimate stage, where the pull of gravity becomes so absolute that not even light can escape the edge of a black hole. The space surrounding these cosmic sinkholes is far from empty. It's a frenzied, swirling maelstrom of superheated gas and dust known as an accretion disk, a place where magnetic fields don't just exist, they rule. This glowing, chaotic whirlpool of plasma is threaded with magnetic fields from the very start, and as the material spirals toward the event horizon, those fields become twisted, amplified, and stretched to their breaking point by the disk's frantic rotation. This isn't a gentle process, it's a gravitational and magnetic wrestling match. The gas in the disk wants to simply orbit forever, held in place by the same principle that keeps planets in their tracks, the conservation of angular momentum. For the black hole to feed, this gas must somehow lose that rotational energy and spiral inward. But how does it shed this momentum? The answer, once again, lies in a powerful magnetic instability. The inner regions of the disk orbit much faster than the outer regions, and this difference in speed acts like a powerful winder, twisting the magnetic field lines that are frozen into the plasma. The field lines tethered to the inner and outer parts of the disk become like taut, elastic bands connecting two runners on a track, one sprinting and the other jogging. This winding creates a magnetic tension that tries to pull the faster inner material backward, slowing it down, while simultaneously pulling the slower outer material forward, speeding it up. This transfer of forces, a phenomenon known as the magnetorotational instability, acts as a cosmic brake and accelerator system. It systematically robs the inner material of its angular momentum, allowing it to fall inward toward the black hole, while transferring that momentum outward to the disk's outer layers. This magnetic friction is the master regulator of the accretion process. Without it, the gas might continue to orbit indefinitely, and the black hole would starve, sitting in darkness at the center of a useless, stagnant ring. But the role of magnetism here becomes even more spectacular. Some of the material spiraling inward doesn't cross the event horizon. Instead, it gets caught up in the black hole's ferocious rotational energy and the unbelievably twisted magnetic field lines that are wound up like a spring near the inner edge of the disk. This coiled magnetic energy finds a way to release itself in the most dramatic fashion imaginable. The intense magnetic pressure and the black hole's spin can launch colossal, focused geysers of plasma perpendicular to the disk, accelerating material to velocities so close to the speed of light that they become what we observe as relativistic jets. These are not gentle outflows, they are the most powerful and efficient particle accelerators in the known universe. The magnetic field acts as both the engine and the barrel of a cosmic cannon. It taps into the immense rotational energy of the black hole itself, and then, through a process of magnetic slinging, it collimates the erupting plasma, squeezing it into two incredibly narrow, opposing beams that can stretch for hundreds of thousands of light years, far beyond the boundaries of their host galaxy. We see these jets blazing from the cores of active galactic nuclei and quasars, where a supermassive black hole is in its most voracious feeding phase. The particles in these jets, spiraling along the tightly wound magnetic field lines, emit a brilliant, piercing light known as synchrotron radiation, a telltale signature of electrons moving at relativistic speeds through a powerful magnetic field. So, when we gaze at an image of a distant galaxy with two enormous jets extending from its core, we are not just looking at a black hole's lunch. We are witnessing the direct and awe-inspiring output of its magnetic power, a force capable of orchestrating the flow of matter on a galactic scale and launching fiery projectiles across the cosmos. So far, we've traced the signatures of magnetism from the hearts of planets to the swirling disks around black holes, but this magnetic tapestry extends to the very largest canvas imaginable, the cosmic voids between galaxies and the vast, seemingly empty intergalactic medium. It's here that we encounter one of the most profound and stubborn puzzles in modern cosmology. Astronomers have discovered, through the subtle polarization of light from distant quasars and the faint glow of synchrotron radiation in galaxy clusters, that magnetic fields permeate these immense, near-empty regions. They are unfathomably weak, perhaps a billion times weaker than Earth's field, but their mere existence across billions of light-years of void poses a monumental question: how did they get there? The answer forces us to choose between two radically different histories of the cosmos, one that roots magnetism in the universe's first moments, and another that sees it as a later product of stellar and galactic violence. The first compelling theory is the primordial origin. This idea suggests that the seeds of these colossal magnetic fields were sown in the extreme physics of the very early universe within the first fraction of a second after the Big Bang. During the rapid expansion of cosmic inflation, or during subsequent phase transitions as the fundamental forces of nature separated from a unified state, incredibly subtle fluctuations could have generated tiny, weak electromagnetic fields. These wouldn't be the powerful fields we see today, but rather a faint, all-pervading background magnetic field, stretched and diluted by the expansion of the universe but still present in every cubic meter of space. If this theory is correct, then magnetism is as fundamental a feature of the cosmos as the cosmic microwave background radiation. It was literally woven into the fabric of space-time at birth, and the magnificent fields we see in galaxies and stars are just this primordial seed, amplified over time by the dynamo action of swirling plasma. The alternative and equally compelling theory is the astrophysical origin. In this scenario, the early universe was truly magnetically silent. The first magnetic fields were not born from the cosmos as a whole, but were forged locally in the hearts of the first stars and galaxies. Intense processes like supernova explosions, the powerful winds from young stellar populations, and especially the colossal jets from active galactic nuclei would have acted as cosmic bellows. These phenomena can inject magnetized plasma at tremendous speeds far out into intergalactic space, polluting the pristine voids with magnetic influence over billions of years. It's a bottom-up process where small, local magnetic events gradually spread, merge, and weave together to create the large-scale magnetic web we now detect. This is a hotly contested debate because the answer carries immense weight. Confirming a primordial origin would give us a powerful new window into the highest energy physics of the universe's infancy, potentially offering clues about grand unified theories and the nature of inflation itself. It would mean that magnetism is an intrinsic property of the vacuum, a fundamental part of the cosmic landscape. Conversely, if the astrophysical origin is correct, it highlights the incredible, far-reaching influence that stars and galaxies have in shaping their own environment on the largest scales, effectively proving that cosmic ecosystems can magnetize the universe through their own life cycles. The quest to solve this mystery is driving cutting-edge observations, as astronomers use the most sensitive radio telescopes to map the faintest magnetic signatures in the most distant voids, hoping to find a pattern that only one of these two cosmic stories can explain. This same magnetic dominance that illuminates nebulae and powers jets reveals a far more destructive face when an unlucky object strays too close to a magnetar. We've seen how these fields can sculpt and confine, but they also possess the raw power to dismantle worlds. The force involved isn't the pull of gravity you might expect. It's something far more visceral: magnetic pressure capable of literally tearing a planet to shreds. This theoretical cataclysm, known as tidal magnetic disruption, unfolds with terrifying elegance. Imagine a rocky planet, perhaps a super-Earth several times more massive than our own, on a fateful orbit that brings it within the magnetar's lethal sphere of influence. From a distance of tens of thousands of miles, the gravitational tides would be fierce, but the magnetic assault would be utterly decisive. The planet would be enveloped in a magnetic field quintillions of times stronger than its own weak field. This isn't a gentle embrace, it's an invisible vise. The magnetar's field exerts an immense outward pressure, a force that pushes against anything in its domain. For a solid body like a planet, this creates an intense stress. The side of the planet facing the magnetar experiences a vastly stronger magnetic force than the far side, and this difference doesn't just pull, it stretches. The magnetic pressure effectively acts like a cosmic crowbar, applying a differential force that works to prise the planet apart. But the true devastation begins when the magnetic field interacts with the planet's very substance. The outer layers of the planet, heated and agitated by the immense forces, would begin to ionize, turning into an electrically conductive gas. And once a material is ionized, it becomes frozen to the magnetic field lines. This is the point of no return. The magnetar's field would seize hold of this plasma, and the violent difference in magnetic strength from one side of the planet to the other would generate colossal electrical currents within it. These currents, in turn, create their own magnetic fields that interact chaotically with the magnetar's field, generating intense heating and violent turbulence. The planet wouldn't just crack, it would be systematically unraveled. Its material would be stripped away layer by layer, atomized into a stream of charged particles that are instantly captured by the magnetar's magnetic grasp. This stream of stellar debris wouldn't fall randomly. The powerful, organized field lines act as a cosmic guide rail, funneling the entire disassembled planet directly onto the magnetar's magnetic poles at velocities approaching the speed of light. The result at the point of impact is a cataclysm of almost indescribable energy. As this torrent of planetary material smashes into the magnetar's solid crust at the magnetic poles, it is instantaneously heated to temperatures of millions of degrees. The kinetic energy of the infalling matter is converted into a brilliant, searing flash of X-rays and gamma rays. This would not be a subtle event. Astronomers across the galaxy would witness a sudden, tremendous X-ray flare, a beacon signaling the death of a world. This theoretical scenario transforms our understanding of a magnetic field from a set of passive, invisible lines into a tangible, physical entity with the capacity for ultimate violence. It demonstrates that in the most extreme environments, magnetism is not just an influence, it is a fundamental force of demolition, a power that can overcome a planet's gravitational binding energy and tear it apart, not with gravity, but with the sheer, uncompromising pressure of its own invisible will. Now, let's turn our attention to a cosmic in-between, a celestial object that blurs the line between star and planet and possesses its own unique brand of magnetic personality, the brown dwarf. Often called failed stars, brown dwarfs are fascinating cosmic anomalies. They form like stars from the collapse of a cloud of gas and dust, but they simply don't have enough mass to cross the critical threshold. Their cores never become hot and dense enough to ignite the sustained nuclear fusion of hydrogen, the engine that powers true stars like our Sun. Too massive to be considered a mere planet, yet not massive enough to shine brightly from fusion, they occupy a mysterious middle ground, cooling and fading over billions of years. It was within this curious class of objects that astronomers made a startling discovery. Some of these failed stars, particularly the rapidly rotating varieties classified as L dwarfs and T dwarfs, are capable of generating magnetic fields far more powerful than any planet in our solar system, and they put on an incredible light show to prove it. Using powerful radio telescopes, scientists began detecting intense, periodic radio emissions from these objects, a classic signature of strong magnetic activity. Even more stunning was the subsequent detection of auroral emissions. Imagine the majestic northern lights, but on a scale that would dwarf Jupiter's displays, wrapped around an object that isn't even a true star. This was baffling. In our solar system, aurorae are powered by an external engine, the solar wind. Charged particles from the sun are captured and funneled by a planet's magnetic field into its poles. But brown dwarfs are often isolated, floating freely in the dark space between stars with no stellar wind to batter them. So what is powering these brilliant, planet-sized aurorae? The answer points to a far more self-contained or locally sourced drama. One compelling theory suggests the engine is internal. As a brown dwarf cools, its interior develops strong convection currents similar to a star. When combined with the object's rapid rotation, some spin so fast they complete a full rotation in just a matter of hours. This churning interior can act as a dynamo, generating a powerful global magnetic field. This field, in turn, can accelerate the brown dwarf's own charged particles, its internal supply of electrons and ions, whipping them along magnetic field lines and down into the atmosphere to create a self-powered aurora, a light show that needs no sun. Another captivating possibility involves a gravitational dance with a close orbiting companion. Just as Jupiter's moon Io feeds particles into its aurora, a large, closely orbiting planet or even a binary brown dwarf companion could be providing the fuel. The immense gravity of the brown dwarf could strip material from the atmosphere of a nearby planet, or the gravitational interplay between two brown dwarfs could generate intense electrical currents directly within their magnetospheres. This process, known as an unipolar inductor, would essentially turn the entire system into a colossal cosmic generator, channeling energy directly into the atmosphere to produce the observed auroral glow. This revelation fundamentally changes our understanding of magnetic objects. Brown dwarfs are not merely faint stars or overgrown planets. They are a unique hybrid, a third category of celestial body that can generate star-strength magnetic fields and produce planet-like aurorae through entirely novel mechanisms. They are a brand new class of magnetic entity, proving that the universe's magnetic creativity extends far beyond the familiar realms of stars and planets. This gradual slowing of a star's spin over its lifetime is a direct consequence of the very same magnetic fields that can, in other contexts, unleash such spectacular violence. The process is known as magnetic braking, and it acts like a gentle but persistent cosmic hand, placing a steady drag on a star's rotation from its fiery youth to its quiet old age. To understand how this works, picture a young, newly formed star. It is a frenzy of activity, spinning at a tremendous rate, sometimes completing a full rotation in just a day or two. This rapid spin is a direct inheritance from the collapsing cloud of gas and dust that gave it birth, a result of the conservation of angular momentum, much like that ice skater pulling their arms in to spin faster. But a young star is not an isolated object spinning in a perfect vacuum. It is an energetic powerhouse, and it is constantly blowing a stream of charged particles out into space. This is the stellar wind, a continuous supersonic flow of mostly electrons and protons that emanates from the star's outer atmosphere or corona. Now, here is where the magnetic field becomes the crucial link in the braking process. The stellar wind is made of charged particles, and charged particles are fundamentally tied to magnetic field lines. The star's powerful magnetic field is frozen into this outflowing plasma, like strands of an invisible spider web embedded in the wind itself. As these magnetically tethered particles are flung outward, they are forced to spiral along the star's magnetic field lines. Because these field lines are, in a way, still anchored to the rotating star, the particles must corkscrew their way out, and this spiraling motion requires rotational energy. In essence, the escaping wind particles act like a long, invisible leash. As they are cast off, they tug on the star's magnetic field, and that tug exerts a torque that works against the star's direction of spin. This process systematically carries away angular momentum, the property that keeps the star rotating, and as that momentum is lost to the vastness of interstellar space, the star has no choice but to slow down. It's a brilliantly efficient and elegant mechanism, a form of cosmic friction that doesn't require physical contact, only the invisible connection of magnetism. The effect of this magnetic braking is most dramatic when we compare stars of different ages. A newborn star, only a few million years old, can be a veritable whirling dervish, spinning so fast its equator bulges outward. But over hundreds of millions to billions of years, the relentless drain of angular momentum by the magnetically coupled stellar wind takes its toll. Our own Sun provides the perfect case study. As a middle-aged star at 4.6 billion years old, it now takes a relatively sedate 27 days to complete a single rotation at its equator. Yet, when we look at young Sun-like stars in distant clusters, we see them spinning several times faster. By measuring the rotation rates of thousands of stars of known ages, astronomers have been able to chart a clear and unmistakable pattern. Stars spin down as they get older, and the primary engine for this spin down is magnetic braking. This relationship is so reliable that astronomers can actually use a star's rotation period as a fairly accurate clock to estimate its age, a technique known as gyrochronology. This process is not just a minor detail, it has profound implications for the star's long-term evolution and the environment of any planets that may orbit it. A slower rotation means a less active magnetic dynamo inside the star, which in turn leads to a weaker magnetic field and a less intense stellar wind over time. This gradual calming of the star's magnetic personality means fewer powerful flares and coronal mass ejections battering its planetary system. For the potential development of life on an orbiting world, this magnetic braking and the resulting stellar spin-down could be a critical factor, creating a more stable and less radiation-blasted environment as the star and its planets mature together. But to fully appreciate the Sun's magnetic influence, we need to pull our perspective far back to the very edge of the solar system's sovereign territory. The Sun doesn't just send out a stream of particles, it inflates a colossal protective bubble around itself and all its planetary children. This immense structure is known as the heliosphere, a vast region of space dominated by the solar wind and the Sun's magnetic field. It's our solar system's primary defense against the true interstellar medium, the thin, pristine gas and dust that fills the galaxy. The shape and structure of this bubble, however, isn't a perfect sphere. It's sculpted into a complex, dynamic shape by two opposing forces, the constant outward push of the solar wind and the pressure from the interstellar material through which our entire solar system is moving. This motion is key to understanding one of the heliosphere's most defining features. As the Sun travels through the galaxy, the heliosphere is compressed on its leading edge like a boat plowing through water and stretches out into a long comet-like tail on the trailing side. Within this entire teardrop-shaped volume, the Sun's influence is supreme, and its magnetic field weaves a pattern of stunning complexity. Because the Sun rotates, completing a turn about once every 27 days, it acts like a cosmic garden sprinkler, spinning as it sprays. The solar wind, carrying the Sun's magnetic field frozen within it, doesn't radiate outward in straight lines. Instead, it gets dragged into a majestic, spiraling pattern. Picture a ballerina spinning while tossing out ribbons. The ribbons would naturally form a spiral as they extend away from her. This is precisely what happens to the Sun's magnetic field as it's carried into space. Near the Sun, the magnetic field lines still exhibit a roughly radial structure pointing directly away from the star. But as you travel farther out, the Sun's rotation twists these lines into an ever-tightening spiral. By the time this magnetic pattern reaches the orbit of Earth, the field is already angled about 45 degrees from the radial direction. By the distance of Jupiter, it's almost entirely wrapped around, pointing more in the direction of the Sun's rotation than directly away from the Sun itself. This grand, sweeping magnetic architecture is called the Parker spiral, named after the astrophysicist Eugene Parker who first predicted its existence. It is the fundamental magnetic skeleton of our entire solar system, a testament to how a rotating star imprints its motion onto the very fabric of its domain. For decades, the detailed structure of the heliosphere and the precise location of its final frontier were matters of theory and indirect observation. That all changed with the incredible journeys of the two Voyager spacecraft. Launched in 1977, these intrepid robotic explorers were designed to study the outer planets, but their missions were far from over once they passed Neptune. They became humanity's first interstellar messengers, tasked with finding the boundary where the solar system ends and interstellar space begins. This boundary is known as the heliopause. It's not a solid wall, but a dynamic, porous transition zone where the outward pressure of the solar wind finally balances against the inward pressure of the galactic wind, the combined material and magnetic fields from between the stars. As the Voyagers traveled farther than any human-made object had ever gone, their instruments told a story of a gradually changing environment. The density of solar wind particles began to drop, and the number of cosmic rays from outside the solar system started to increase. Then, in 2012, Voyager 1 sent back the historic data. It had crossed the heliopause. The telltale signs were unmistakable: a dramatic drop in the particles from the Sun and a corresponding surge in cosmic rays from the galaxy. Voyager 1 was no longer inside the Sun's magnetic bubble. It was floating in the interstellar medium. Voyager 2 followed suit, crossing the heliopause in 2018 at a different location, confirming that this boundary is not a perfect sphere but a rippling, asymmetrical surface shaped by the turbulent pressures of the galaxy. The data from these crossings revealed that the heliosphere is our first and most important cosmic shield. It deflects and moderates the flow of galactic cosmic rays, which are high-energy atomic nuclei accelerated by distant supernova and other violent events. Without the heliosphere's buffering effect, the radiation environment throughout the inner solar system would be significantly more intense, potentially influencing planetary climates and posing a greater challenge for the emergence of life. The ongoing journey of the Voyagers, now in true interstellar space, continues to send back priceless data about this mysterious region, helping us understand the final, fading echo of our Sun's magnetic will as it merges with the magnetic currents of the wider Milky Way. While we often picture our planet's magnetic field as a stable, protective bubble, its far side is a scene of constant, violent rearrangement, a place where the steady pressure of the solar wind forges a region of immense stored energy. On the side of Earth opposite the Sun, our magnetic field doesn't simply end. It is stretched and pulled into an extraordinarily long, comet-like structure called the magnetotail, which extends for hundreds of thousands of miles into the deep darkness of space. This tail is formed as the solar wind, that continuous stream of charged particles, flows around our magnetosphere and drags the magnetic field lines from the day side, sweeping them back over the poles and far out into the night side. Think of it like a cosmic windsock, with our planet at the narrow end and a vast, elongated tube of magnetic influence streaming out behind us. Within this immense magnetotail, the field lines are stretched taut, running largely parallel to each other in opposite directions, northward on the top of the tail and southward on the bottom, separated by a thin, seething layer of plasma known as the plasma sheet. This configuration is inherently unstable, a loaded spring waiting for a trigger. That trigger is the phenomenally powerful and fundamental process of magnetic reconnection. In the neutral sheet at the center of the tail, where the oppositely directed magnetic fields are pressed closely together, the conditions become ripe for a catastrophe. The highly conductive plasma trapped here allows the magnetic field lines to break, much like overstretched elastic bands snapping under tension. But they don't just disappear, the broken ends immediately and frantically seek a new, lower energy state. They cross-connect with each other, forming new, relaxed loops that snap back violently toward Earth, while the disconnected sections are ejected downstream away from the planet. This sudden reconfiguration is not a gentle event. It converts a colossal amount of stored magnetic energy into explosive heat and kinetic energy in a matter of minutes. The plasma particles caught in this event are catapulted to incredible speeds, accelerated to energies that can power the magnificent auroral displays we see at the poles. Much of the material from the plasma sheet, now superheated and energized by the reconnection process, is hurled down the newly reconnected magnetic field lines in a tremendous surge toward Earth's poles. When these particles slam into the upper atmosphere, they excite oxygen and nitrogen atoms, causing them to glow in the spectacular curtains of green, red, and purple that dance across the polar skies. This is a direct, physical link between a magnetic explosion happening hundreds of thousands of miles away in the void and the beautiful light show we witness from the ground. But the consequences of this magnetic reconnection extend far beyond the creation of aurorae. These events are the primary drivers of the intense, planet-wide disturbances we call geomagnetic storms. A major reconnection event in the magnetotail injects a huge amount of energy and charged particles into Earth's inner magnetosphere, dramatically altering the entire system's delicate equilibrium. The radiation belts swell with dangerous, high-energy electrons, and powerful electrical currents begin to flow in the ionosphere. It is these induced currents that pose a direct threat to our modern technological infrastructure. During a severe geomagnetic storm, these currents can find their way into long conductors on the ground, such as high-voltage power transmission lines. The power grid, designed for 60 Hz alternating current, can be massively disrupted by these slow, direct currents, which can cause transformers to overheat, saturate, and even fail catastrophically. The most famous historical example, the Carrington event of 1859, caused telegraph systems, the advanced technology of the day, to fail across the globe, with operators reporting sparks flying from equipment and papers setting ablaze. A storm of that magnitude today would have a devastating impact, potentially causing widespread, long-lasting power blackouts, disrupting satellite communications and GPS navigation, and crippling financial and transportation networks. This makes the study of magnetic reconnection in our own magnetotail not just a matter of scientific curiosity, but a critical area of research for space weather forecasting, as we work to understand and predict these invisible explosions that connect the dynamics of the Sun directly to the stability of our society. But even the universe's most fearsome magnetic monsters must ultimately bow to a deeper set of rules, a fundamental ceiling written into the very fabric of reality by quantum physics. We've explored magnetars with fields 1,000 trillion times stronger than Earth's, but there exists a theoretical upper limit, a point where a magnetic field becomes so potent that it ceases to be just a force and begins to fundamentally reshape the nature of nothingness itself. This absolute boundary is known as the Schwinger limit, or the quantum critical field strength, and it stands at approximately 4.4 times 10 to the 13th Gauss. To grasp the sheer extremity of this number, consider that the most powerful magnetic fields we can sustainably create in laboratories on Earth are about 100,000 Gauss. The Schwinger limit is over 1 billion times stronger than that. Even a typical magnetar's field, for all its mind-bending power, sits just a factor of 10 or so below this ultimate ceiling. This isn't an engineering limit, it's a fundamental one arising from the bizarre and counterintuitive laws of quantum electrodynamics, our most precise theory of how light and matter interact. At this staggering intensity, the magnetic field's influence becomes so overwhelming that it starts to directly manipulate the quantum vacuum. We often think of a vacuum as pure, empty nothingness, but quantum physics tells us it's actually a seething, bubbling sea of virtual particles. These are particle-antiparticle pairs, like electrons and positrons, that constantly flicker into and out of existence for imperceptibly short moments, borrowing energy from the vacuum before annihilating and returning it, all in accordance with Heisenberg's uncertainty principle. In a normal magnetic field, this quantum froth remains invisible and undetectable. But when the field strength approaches the Schwinger limit, something extraordinary happens. The field provides such an immense amount of energy that it no longer needs to be borrowed. It can spontaneously rip these virtual pairs out of the vacuum and turn them into real, observable particles. The magnetic field literally catalyzes the creation of matter from pure energy, causing space itself to boil with a mist of newly born electrons and positrons. This isn't a theoretical curiosity. It's a direct prediction that, if we could ever observe it, would represent the ultimate domination of energy over the quantum realm. This process also warps the very behavior of light in a phenomenon known as vacuum birefringence. In a normal medium, birefringence occurs when light splits into two rays traveling at different speeds, like what happens in certain crystals. But here, it's the vacuum of empty space that becomes birefringent under the influence of this hyper-strong magnetic field. Photons, the particles of light, have a property called polarization, which describes the orientation of their oscillating electric and magnetic fields. When light travels through a magnetic field at the Schwinger limit, photons polarized parallel to the field will interact with the sea of virtual particles differently than those polarized perpendicular to it. This difference in interaction means the two polarizations will actually travel at slightly different speeds. The vacuum itself, once thought to be a uniform void, becomes an exotic optical material, slowing down one type of light more than the other. This effect is so subtle that it requires unimaginable magnetic fields to manifest, but for a hypothetical observer near a magnetar, the very fabric of space would act like a giant cosmic crystal, subtly distorting and polarizing the light from any background star. The quest to find observational evidence for these extreme quantum effects is one of the most exciting frontiers in high-energy astrophysics. While we cannot yet create such fields in a lab, the cosmos provides us with natural laboratories in the form of magnetars. Astronomers use powerful X-ray and gamma-ray telescopes to study the light emitted from these objects, searching for the unique polarization signatures that would be the smoking gun for vacuum birefringence. Detecting this signal would be a monumental achievement, providing direct experimental confirmation of a key prediction of quantum electrodynamics in a regime we can never hope to test on Earth. It would show us that the laws of physics, even in their most extreme and alien manifestations, remain consistent and predictable, and it would give us a profound new window into the intimate, turbulent relationship between energy, matter, and the empty space that holds them all. This enduring legacy of magnetic fields brings us to a fascinating and beautiful class of stars that act as cosmic archivists, preserving a magnetic memory from a time long before their current state. Scattered across the galaxy among the hot, brilliant A and B-type stars are peculiar varieties known as AP and BP stars. These aren't just ordinary suns, they are stellar magnets of a completely different nature. Our own sun generates its magnetic field through a churning, turbulent dynamo in its outer convective layer, a process that makes its field complex, chaotic, and constantly changing, with a cycle of activity that flips every 11 years. But the AP and BP stars operate on a fundamentally different principle. They possess strong, globally organized, and remarkably stable magnetic fields that can be thousands of times more powerful than the Sun's. Imagine a star with a magnetic field so structured and steady that it resembles a simple, gigantic bar magnet floating in space with clear north and south magnetic poles. This order and stability are the key clues that point to an ancient origin. These are not dynamo-generated fields, they are what scientists call fossil fields. Think of them not as a living, breathing magnetic personality like the Sun's, but as a perfectly preserved relic, a magnetic fly trapped in stellar amber. The leading theory suggests that this powerful magnetic field is a remnant from the star's very formation. As the vast cloud of gas and dust collapsed to create the star, the weak, interstellar magnetic field that was woven through that primordial cloud could have been concentrated and frozen into the newly born star's radiative interior. In stars like these, the outer layers are stable and don't have the turbulent convection needed to run a solar-style dynamo. This lack of internal churning is what allows the fossil field to survive for millions, even billions of years, unchanging and dominant, a direct messenger from the star's birth. An alternative and equally compelling theory proposes that these fields could be the product of a dramatic stellar merger in a binary system, where the violent collision and mixing of two stellar cores could have generated a powerful, organized magnetic field that then became locked into the resulting single star. This fossil field hypothesis provides an incredibly clean laboratory for astronomers. By studying these stars, we can investigate the pure effects of a strong magnetic field without the complicating noise of an ongoing dynamo. The field itself becomes a powerful tool, sculpting the star's atmosphere in unique ways. Because the field is so strong and structured, it influences the diffusion of elements within the star's outer layers. Heavy elements like silicon, strontium, chromium, and rare earths are drawn toward the magnetic poles by the field's influence, while lighter elements like helium float away from these spots. This creates strange, patchy surfaces with giant chemical spots, continents of exotic elements that rotate into and out of our view. As the star spins, we see the brightness and spectral signature of these elements change in a perfectly repeating cycle, allowing us to map not only the star's magnetic geometry, but also its bizarre surface chemistry. This makes AP and BP stars celestial Rosetta Stones, helping us decipher how magnetic fields can shape the very composition of a star and giving us a direct glimpse into the magnetic conditions that were present when these stellar giants first ignited. All of this magnetic power across the universe, from the violent chaos of magnetars to the steady churn of planetary dynamos, brings us to a profound and deeply personal question. What does magnetism have to do with us? The answer may be everything. In our ongoing search for life beyond our own world, we tend to focus on the obvious prerequisites, a planet orbiting within its star's habitable zone, where temperatures are just right for liquid water to exist on the surface. But nestled within that comforting orbital band, another invisible factor could be the ultimate decider between a living world and a barren wasteland. A stable, global magnetic field isn't just a cosmic accessory. It appears to be a fundamental pillar of long-term planetary habitability, a silent guardian whose presence or absence could make or break the delicate chemistry of life. Its most critical role is as a planetary shield. A world without a strong magnetosphere is like a fortress with its gates wide open, completely exposed to the relentless barrage of its parent star's stellar wind. This constant stream of charged particles doesn't just wash over the planet. It actively strips the atmosphere away, molecule by molecule, in a process known as atmospheric erosion. The solar wind carries its own magnetic field, and when it slams into a planet's upper atmosphere, it can energize the air particles, giving them enough of a kick to escape the planet's gravity entirely. Over hundreds of millions of years, this slow-motion sandblasting can drain a world of its life-sustaining blanket of air. We see this tragic story written across the surface of our neighboring planet, Mars. Billions of years ago, Mars was a warmer, wetter world with rivers and lakes, and geological evidence strongly suggests it once had a global magnetic field. But when that magnetic dynamo shut down, its protective shield vanished. The solar wind, unimpeded for eons, systematically scoured away most of the Martian atmosphere, turning it into the cold, thin-air desert we observe today. Its water evaporated and was lost to space, and any chance for a vibrant surface biosphere likely vanished with it. Earth, by stark contrast, has maintained its magnetic shield for billions of years, and as a direct result, it has held onto its thick, nurturing atmosphere, allowing life to not only emerge but to flourish and diversify. This protective role extends far beyond just holding onto the air we breathe. A magnetosphere is also our primary defense against harmful cosmic and stellar radiation. The surface of a planet without this shield would be bombarded by high-energy particles that can shatter the complex organic molecules that are the building blocks of life. This radiation doesn't just threaten life itself, it can also prevent it from ever getting started by breaking down the delicate precursors in the primordial soup. On Earth, our magnetic field acts as a cosmic umbrella, deflecting the majority of these damaging particles and channeling the rest toward the poles, where they create the beautiful, harmless aurorae far above the surface. This radiation shielding creates a safe environment at the ground level where fragile biochemistry can experiment, evolve, and ultimately thrive without being constantly torn apart. For this reason, when astrobiologists draw up their checklist for a potentially habitable exoplanet, the presence or likelihood of a strong magnetosphere is moving from a background consideration to a frontline factor. Detecting a magnetic field on a world light years away is incredibly challenging with our current technology, but it's not impossible. One promising method is to look for the telltale signs of stellar wind interaction. If a planet transits or passes in front of its star from our viewpoint, sophisticated instruments could potentially detect the faint, extended signature of a magnetosphere, a protective bubble of magnetized plasma slightly altering the starlight. Another clue could come from radio emissions. Jupiter, for instance, produces powerful radio waves through its interactions with its moon Io, a process driven by its magnetic field. A sufficiently sensitive radio telescope might one day pick up a similar signature from a distant exoplanet, a clear broadcast announcing the presence of a magnetic shield. So, while we gaze at the twinkling lights in the night sky and wonder which ones might host living worlds, we should remember that the most important ingredient for life might not just be liquid water, but the invisible, protective embrace of a magnetic field, a force that turns a mere rock in space into a sanctuary. As we stand on the precipice of a new era in astronomy, the future of magnetar study promises to peel back the layers of these magnetic enigmas in ways we've only dreamed of, using tools that will transform our cosmic perspective. The next generation of observatories, both on the ground and in space, are being designed with the explicit goal of probing these extremes, turning the faint whispers of the universe into a clear, roaring conversation. Leading this charge is the Monumental Square Kilometre Array, or SCAR, a revolutionary radio telescope network that will be the most sensitive ever built. When its thousands of dishes and antennas across South Africa and Western Australia are fully operational, the SKA will act as a cosmic hearing aid, allowing us to detect the faint, steady radio pulsations from magnetars that are currently too distant or quiet to hear. More importantly, it will be able to monitor the entire sky with an unprecedented rapid cadence, giving us a real-time movie of magnetar activity. This means we won't just study these objects in snapshots, we'll watch their magnetic personalities evolve over days, weeks, and years, potentially catching the subtle radio precursors to a giant flare, a warning signal from across the galaxy that the star is about to unleash its fury. The insights won't stop at radio waves. In the high-energy realm, proposed advanced X-ray observatories are set to revolutionize our view. missions concepted to succeed current telescopes like Chandra and Newton will carry instruments with vastly improved resolution and sensitivity. Imagine being able to map the hotspots on a magnetar's surface as it experiences a starquake, watching in real time as the crust fractures and the magnetic field reconfigure, all by analyzing the minute changes in its X-ray glow. These observatories could even detect the specific polarization of X-rays coming from a magnetar, a measurement that would serve as the definitive proof for vacuum birefringence, the phenomenon where a hyper-strong magnetic field turns the vacuum of space into a bizarre crystal that bends light. Catching that signal would be a direct validation of quantum electrodynamics in a regime no Earth lab can ever replicate, confirming that the laws of physics hold true even in the most distorted corners of reality. This multi-messenger approach, using every form of light from radio to gamma rays, will paint the most complete portrait yet of a magnetar's life cycle, from its turbulent birth to its eventual magnetic decay. But perhaps the most profound new window into these objects won't rely on light at all. The future of magnetar science is inextricably linked to the nascent field of gravitational wave astronomy. When a magnetar's crust shatters in a violent starquake, the event doesn't just release a flash of light. It sends literal ripples through the fabric of space-time itself. These gravitational waves are a direct probe of the star's interior, carrying encoded information about the rigidity of its crust, the dynamics of its superfluid core, and the very equation of state of ultra-dense matter. Current detectors like LIGO and Virgo are already sensitive enough to potentially detect a giant flare from a nearby magnetar within our galactic neighborhood. The next generation of ground-based detectors like the Einstein telescope and future space-based observatories like LISA will be sensitive to a much wider range of frequencies, allowing them to listen for the gravitational hum of smaller, more frequent quakes on magnetars much farther away. By combining the gravitational wave signal with the simultaneous flash of X-rays and gamma rays, we will be able to do something previously unimaginable: perform a cosmic ultrasound on the neutron star. The gravitational waves will tell us about the interior rumble, while the electromagnetic radiation shows us the surface explosion. Comparing the two will reveal exactly how the energy propagates from the fractured crust down into the quantum strange matter of the core and back out again. This could finally answer enduring questions about what exactly lies at the heart of a neutron star, whether it's a soup of free quarks, a crystal of exotic particles, or something even more bizarre. Each magnetar flare, then, becomes more than just a spectacular light show. It becomes a key, unlocking the secrets of matter compressed to densities that defy our very understanding, teaching us about the fundamental building blocks of the universe in a way that no particle accelerator on Earth ever could. The coming decades will transform these magnetic monsters from distant, theoretical curiosities into intimate cosmic laboratories, where the most extreme physics becomes observable, testable, and finally understood. From the gentle pull of a refrigerator magnet to the star-shattering fury of a magnetar, our journey across the cosmos has revealed one stunning truth: magnetic fields are the universe's silent architects. They are the threads woven through the fabric of reality, a fundamental and dynamic force that sculpts the cosmos at every conceivable scale. We've seen how our own planet's protective magnetic bubble is a perfectly tuned life support system, a steadfast guardian that deflects lethal radiation and holds our atmosphere securely in place, creating the safe harbor where life could take root and flourish. Yet this same gentle force, when amplified by the universe's most violent factories, becomes a titan of creation and destruction. Within the swirling disks of newborn stars, magnetic fields act as cosmic choreographers, guiding the flow of gas and dust to build worlds. In the chaotic hearts of distant galaxies, they launch jets of matter that stretch for hundreds of thousands of light years, shaping the evolution of entire galactic neighborhoods. And in the ultimate extremes within the city-sized hearts of magnetars, these fields twist the vacuum of space itself into a bizarre quantum medium, bending light and tearing worlds apart with pressures strong enough to overcome gravity itself. This isn't a story of a single, simple force. It's a symphony of magnetic influence playing out from the smallest plasma currents to the grandest structures in the cosmos. Every flicker of an aurora, every pulse from a spinning pulsar, and every brilliant flash of a gamma-ray burst is a note in this cosmic composition, reminding us that magnetism is as vital to the universe's story as gravity or light. Our exploration is far from over. With every new observation from revolutionary telescopes and gravitational wave detectors, we peel back another layer of this magnetic mystery, uncovering secrets about the nature of matter, energy, and the very fabric of space and time. The universe's magnetic story is still being written, and each discovery pushes the boundaries of what we thought was possible. We'd love to hear which of these magnetic marvels resonated most with you. Was it the thought of a planet being unraveled by invisible forces, or the profound protection offered by our own world's magnetic shield? Let us know in the comments below what amazed you the most. If you enjoyed this deep dive into the cosmos's invisible power, be sure to subscribe and hit the notification bell so you don't miss our next journey into the universe's greatest mysteries.